European Coordinating Committee for AI. We have Malik Ghallab with us this morning. Malik is a directeur de recherche at l'AS in beautiful Toulouse, France, which is part of the government CNRS research lab system. Malik previously served as director of the lab and also as the executive officer for R&D and technology for INRIA, the French government informatics research lab system. He has served in formulating the French national research policy. He is a Chevalier of the French Legion of Honor. He is an ICAPS fellow. And as many of you know, Malik has been extraordinarily influential as a community builder in artificial intelligence and especially in planning. He served as the president of ICAPS at its incorporation and literally wrote the book on automated planning with his popular textbook with Dana Now and Paolo Traverso. His planner ICSTET pioneered many influential techniques in temporal planning and execution, and his current passion is to connect planning with acting. And that's particularly appropriate for our conference this year with our emphasis on robotics. So please join me in welcoming Malik Ghallab.
Many thanks, Wheeler, for this very kind introduction and for the kind invitation to speak at ICAPS. It's becoming a real challenge to speak at ICAPS. So many wonderful talks and a lot of things happening with singing, dancing. I was not prepared to do any singing. I tried this morning to go through the lyrics that York sent, but I didn't find the word acting or the word execution, so I couldn't get started. So it's a great opportunity for me to further promote the actor's viewpoint in our field and to tell you about some of the problems that arise when you try to couple planning and acting. So in many scientific fields, it is believed that the most pressing challenges are not in the specialized disciplines, but in the problems that arise in coupling phenomena that are studied in these disciplines. This is true in life science, this is widely illustrated in environment sciences, and I would like to convince you that this is also the case in the problems in our field for coupling, planning, and acting. This talk is not about a focused technical result or set of results. It is more a vision, an informal vision to advocate for these challenges and to provoke questions than to offer answers. Planning and acting is a very long story, long and finished, I believe. It goes back to the early beginning of the field with PlanX, the PlanX system. Let's see, who's familiar with PlanX? Wow, less than 10% of the audience. Whereas the planning counterpart of PlanX is mentioned in the proceedings of this conference 174 times. The planning counterpart of PlanX being STRIPS. So how come that we do not teach enough the execution part in planning? And what we should do in order to take into account these aspects. Here is the first paper entitled Planning and Acting that I found. It is due to Drew McDermott. I saw McDermott in the conference yesterday. If he's in the audience, I would like to greet him this morning. This paper by Drew goes back to 1978. He takes a problem-solving point of view that I'm not going to develop here, but he starts with an interesting list of problems that he tried to address in this paper. The first one is block stacking and Tower of Hanoi, kind of examples that is widely solved. The last one, I don't know, for those of you who can read, is a tough marital issue that is probably widely open, and the kind of the kind of problems that I am interested in sit somewhere in between and are illustrated mostly with robotics examples. I would like to acknowledge a collaboration with Denano and Paolo Traverso and the collaboration with Félix Ingrat. Félix is standing over there. Hi, Félix. And this collaboration led to two papers, two recent papers where you can find more about the points that I'm developing this morning. As customary, the good ideas in this talk, if any, stem from these collaborations. The bad ideas are mine. So I'll try to convince you if there is a need that acting is different from execution and that acting is different from planning because it has some specifics in terms of word models and semantics of actions that we can try to address to a hierarchy of state spaces and action spaces with two classes of action models, descriptive and operational models. And I'll exemplify these through refinement methods and how to do that, then I'll conclude. So planning is certainly concerned with acting. We keep talking about actions. We model them, we search through them in order to build up plans, and we reason on these actions. I contributed to this sentence some 10 years back, but I believe it's not entirely correct. It should say that planning is one of the reasoning sides of acting. It's not the reasoning side. So we keep talking about acting, but most of the time we abstract away acting as a label on edges, which is very legitimate in some cases, but it reduces the spectrum of problems and it limits the effectiveness of approaches that you can handle by doing such abstraction. So can we do planning without acting? Obviously, yes. Many of us, including myself, have survived for decades without considering acting, and this is legitimate to advanced part of the field, and also it is legitimate to address applications that have no acting problems, that are not concerned with acting because there is no acting in them, or because the acting will be done by someone who is able to deliberate, in particular a human. And a good example of that are design applications, design of devices, systems, and procedures. I was involved with a couple of friends in a startup company some 15 years back, and we carefully avoided acting problems by tackling this kind of design applications. The company has not been bought by Amazon, but has been bought by Siemens and is still doing business, and it's very focused and effective kind of techniques that are widely useful. In this kind of application, you are interested in docking and folding problems in proteins and how to extract a molecule from some given site. Here's some sugar enzyme, and you are not going to act. You would like to understand it to better model with motion planning techniques. So these are illustrations where you do not need to consider acting. But in many other cases, you do have acting problems, and they may or may not be coupled with planning. And when they are coupled, this coupling can be relevant from an AI point of view. So when are these coupling problems relevant to us? Probably not here. If you are designing a vending machine, even a complex one, you may have some interesting planning problem, in particular at the design time, some interesting acting problems that you solve with the appropriate automata, but you do not have coupling problems between them. Now, if your vending machines start wandering around and seeking from customers, you may get into some coupling problems. We have had very impressive illustrations of 2 days ago by the talk of Peter Woermann about how you can decouple planning and acting by correctly engineering the environment and tackling with the appropriate tools the two levels of planning and acting that reduces mostly to execution with the error handling and so on, and intervention of maintenance when there is a need. So when is decoupling unfeasible? What are the cases where you cannot do these kind of things? Well, when you cannot engineer the environment, that is when acting is different from execution, and this is the case for autonomous deliberate actions. The two words, autonomous and deliberate, are important. So deliberate actions are purposeful, justifiable actions with respect to some goals. You build up plans to have these justifications. You do not need to deliberate if your system is restricted to a single task or single environment, or an environment that you have engineered correctly. As I mentioned, these kinds of examples do not need deliberation. They live within some ecological niche. Their hardwired innate behavior, even if you can reprogram it, does not need deliberation. It can be quite sophisticated and effective. You may require planning techniques to design it, to reprogram it. Planning techniques can be very useful, but you don't need deliberation at the acting time. So if you have changes in your environment and tasks, you have to get out of the niche and then deliberation is needed for you. So the intuitive argument of why acting is different from execution is the following. Diversity in environment and tasks entails deliberation, and deliberation means knowledge reasoning, and the more knowledge and reasoning you have, the better and the more robust and effective is your behavior. And you know more at the acting time, at the planning time. This has been illustrated in several talks at this conference. You know more because the knowledge is not available, because it's too costly to build, and so on. Consequently, acting with diversity demands deliberation at acting time, because this is where you have the knowledge to be able to deliberate. This is illustrated in many cases. The simple example of open door that is very easy to plan with is very difficult to actually carry on, because there are wide diversity of doors, of door handle, of ways to opening doors, of doors that open left, right, towards or away of the opener, door that slides, and so on. So this intervention and robot of GPL NASA opens the door in a teleoperated way. It does not do it autonomously. Here is an even simpler example. Do I need to deliberate when I'm walking and I have planned my trajectory? Most of the time, no. When I have planned my trajectory, I don't need to deliberate. But on a rough ground, rougher than this, what's in here, the gauge stabilizer of this robot that developed by ACE is not sufficient. And the robot needs to further deliberate than just motion planning. And this is really the simplest example that you can think of. As soon as you have to carry something, the ground is rougher and start moving or so on, you have to deliberate. So acting is different from execution in a number of application domains. I mentioned rescue and exploration robots in the previous slide. Service and personal robots have been widely illustrated in this conference, and in particular in the robotics track and the PlanRob workshop. You have to do interactions in very rich semantically environments and diverse environments, and you need to deliberate at the acting time because you do not have the knowledge. But it's not only for robotics. Serious games where you have to train a professional for a wide diversity of situations and tasks offer also good examples, and there are certainly other examples. So if acting requires deliberation at the acting moment, why don't you specify your acting problem as your acting problem as a planning problem at that appropriate level and do with planning techniques? Certainly, you can do that, and planning techniques are useful and very relevant for deliberate actions, but I would like to convince you that there are specific problems that make acting different from planning. What are they? Well, planning, we know how to define that as mapping from domains and problems into plans, and you get domains and problems as input, and you provide the plan as input, and you do that through prediction and search. So you predict what will be the next state if you carry on this action in that state, and you search through your possible actions in order to find a way to achieve your goal. And by the way, we have oversimplified predictions and invested a lot in search, which make our search part of the technology quite developed, but we need to further invest in prediction to be able to address more diverse semantics of actions and more complex actions, even at the cost of search in some cases. So this is for planning. Acting is not a mapping from something to something. It is a situated interactions between an input-output stream of things that interact with an open environment. You need these situated interactions to be able to adapt your action to context and to react to context. So this is a function, and this cannot be described as a function. It is more properly described as a transduction. And transductions are different from functions. So I believe that I can hear a number of objections to this argument. The first objection is say, well, you need a situated interactions. Why don't you synthesize right from the beginning a situated automata and act with that? Yes, we know how to do that with MDP, non-deterministic planning techniques, and so on. However, if you really would like to handle all the diversity of the environment that you can meet, your prediction functions become much more complex. It is a function of your state, your actions, and the events. And it can be exponential in the number of possible effects and the number of possible events. And if you take into account durative actions with time, this coupling of actions and events become even worse. And I'm talking here only about the modeling effort that becomes tremendous in addition to the complexity, computational complexity problem. So most of the time, you reduce the level of diversity that this kind of automata cope with, and you have to add some adaptation of your automata to the executional diversity. And you are back to my original problem. The second objection that I hear is, well, you need a closed loop here. Why don't you close the loop, add some controller, and close the loop on the environment? Certainly, we have done so, and with some success, with techniques such as receding horizon, interleaved planning and execution, and this works fine in a number of applications, and we should really keep paying attention to these kind of things. However, it is very difficult to get the usual input of a state and a goal. The type of input is not always a state and a goal from your environment. You have things to which you react and so on. Moreover, and more importantly, the type of models that you have here and the type of models that you need here are of different nature. And this is something, in my viewpoint, more important than the first point. And the third argument that I hear is, okay, acting is different from planning, but it is someone else's business. Why don't you design your acting system as a flexible embedded system? Use control theory, use automata theory, use real-time reactive systems, synchronous languages. Many excellent developments have been done with that. For example, flight management systems with synchronous languages. You have millions of codes that have been that behave well and have been proven in a satisfactory way. These flight management systems, in a rough situation, when you have some failure in the airplane, or rough weather, or some external conditions, they are out of the envelope of their design envelope. And you need more deliberative and sophisticated systems, such as the system that David and his colleagues at Ames are developing, or such as the systems that Brian Williams mentions, to be able to cope with the diversity of tasks and environments that you have developed with these systems. Although I should say that some recent developments, such as the behavior programming approach, is trying to further extend the capabilities of this embedded systems technology, and we should keep paying attention to that. So this is the third objection. Now let me take an opinion poll. Who is willing at this point to buy the fact that this inequality holds most of the time? Okay, so I convinced some of you, so I may have to go on and explain the rest, how to cope with them. What are the specifics of acting as a deliberation function and how to address them jointly with planning? In terms of word models and the semantics of actions. Word model. In planning, your knowledge is explicit, one way or another. I know fact phi if the phi is in my state or can be entailed very easily from my state, or easily from my state, let's say. In acting, you have to rely on explicit and implicit knowledge. What I know is reflected into what I am doing, not necessarily into something explicit somewhere in my mind or in some database and so on. It is implicit through my internal state. In addition to things that are explicit, I also do have implicit knowledge. And I have to take care of that one way or another. There were a few proposals, for example, the proposal of Stanley Rosenshine, the theory of situated automata back in the mid-80s, to be able to step back and express this implicit knowledge that is implicit in my internal state of a situated automata in some formal way, not to implement that, but to be able to reason on what an actor is doing. I believe we should carry on this line of work. It has not been pursued as much, to my understanding, in our field. So this is the word knowledge. Now the state update. In planning, in the deterministic case, the state update is very easy. It's just an assignment with respect to your prediction. In acting, assignment is illegitimate. You cannot assign anything to your state. So you have to rely on observation and untied knowledge. So basically, again, to quote from Drew McDermott's paper, if you are designing a physical system, you must treat the real world with respect. And treating the real world with respect, you should keep in mind that S is not your state. It is just simulated state. This is what you fancy, or your planner fancy. This is not the real state. It is a simulated state. And in parallel, you should keep some store of world facts holding, or that hold but are still relevant to you in the past, and you should keep that one way or another, and from time to time when you need to, you update, and very seldom you do this. You may do that with respect to state variables that reflect your own reasoning that are subjective in a way. So our planner and actor system should keep these two in parallel. Now, the world is dynamic, and we are not the only actor in the world, and there are exogenous events. As I mentioned, these exogenous events are very hard to model. We do not have the knowledge, and the modeling is tremendous. So we do without most of the time. Only few events are taken into account, and this is fine at some abstraction level. However, in acting, these are essential components for acting and reacting, because they modify and focus your deliberation, they possibly affect your goals, and you have to react to them. So events are an essential mechanism that distinguish acting from planning. By the way, I would like to mention that an event is not a change, is not only a change in the value of state variable. It is a compound change. It is a compound change of several things that happen that you care about. Open world. You have to face an open world. The closed world assumption is very convenient in planning. It is feasible and reasonable if you are focusing your reasoning on some abstract representation of the world, but you have to keep in mind that it is a simplifying assumption. You have to interact with an open world in order to augment your knowledge with sensing and information gathering action. This is the purpose of deliberating at acting time, but also at planning time with an open world. Open world state and properties that you acquire, but also you change your models. This is something very important, that your models of the environment may change or may get enriched, but also your models of actions. And some examples of this have been developed. Recently, the Robot Earth and the No-Rob in the robotics community. We have had the affordance work that was presented by Iman and Awad yesterday, and at the robotics workshop. So some nice work is going on here, and you need to handle epistemic state variables that tells you what you know, what you don't know, what you can query, and some of this has been done in planning. You have to do that while planning, before and while acting, and I mentioned the PKS system by Petrick and Bacchus, or the Maple system by Brenner and Nebel as examples of things that you can do in order to take into account the open world. So this is at the basis with respect to the word model. Let's see the semantics of actions and how you model actions. So you have two things: choosing and organizing actions for planning and performing actions for acting. Here is a simple example: a pickup object, my service robots of the previous illustrations, very easy to specify in our favorite planning language, and there are plenty of such actions in our domains. I don't need to elaborate. Now, if I have to move on this side and perform the actions, I need to answer to all these questions. Where should I stand to reach for my objects? Which hand to use? How to reach for the object? How to observe the pickup? Which grasps to apply? Where to grasp? What are the parameters of these grasps? How to lift its parameters? How to hold? And so on. This has been nicely illustrated in Leslie Scabling talk on Monday at the PlanRob workshop with very lively illustrations and videos. And I would like to convince all of you that these are really deliberation issues. You will never achieve this task if you do not reason on all these questions and address them through deliberation. No sensory motor system is capable of giving you the answer to these questions, and these questions are related. For example, the way you observe impact the rest, and symmetrically. So let's go through a number of differences between the yellow and the green part. You need to refine your actions into several steps down to the command level. You need to domain-specific representations and parameters. You need concurrency with sensing and reactions. These are often abstracted away in one, and they are essential for two. You need search for both, but in different ways. The domain-specific representations and technique are essential here, and they are becoming considered in one as well. You need a different action organization. Often in here, the action organization is simplified. It is a partial order of actions, or it is a number of timelines on which you handle your constraints, but you need concurrency and closed loops in two. And you have different models and representations here, to which I'll come back later. So these are the specifics. Let's try to address them through two means, or simplify how to address them to three means. One is a hierarchy of state and action spaces, and the other one is two types of action models. The hierarchy of state and action spaces goes back to how do we organize our state space. In planning, fortunately, we don't use a flat state space organization. We did some of that in MDP and non-deterministic planning, but even there, we rely on factored representations, where you basically have a set of state variables ranging over some range, and you can go further and have a structured factored representations with parameterized state variables that offer very expressive languages to tell about the dynamics of your system, assuming that these state variables change over time, and you have models of how they change. And each state variable is mapping from some domain objects to some range. What I'm advocating is to go further and to rely on hierarchized set of state spaces, where a state at some level H is mapped in a deterministic way to a state more abstract, higher up, and to a set of possible states at a lower level. And you can do that easily by defining your state space at this level as being a partition of your state space at that level. That is, each state at this level is a subset of states of this level. And you can define this partition by considering that the domain of your state variables are partitions of the domain of the state variable lower down, or by ignoring some state variables that refine your reasoning lower down. A simple example, the location of my robot range over some space domain, and this space domain is symbolic for some level. I am in New Hampshire, in Portsmouth, in the Sheraton, in the ballroom of the Sheraton. At some point, I go down to geometric coordinates in some reference frame. And I can handle that in a good way through a partition of the sets over which space refer. And I can have a state variable that refer to the pose of my arm in some with respect to some kinematic configurations that is not needed at some level, that refines my state space lower down. I have to take into account different types of domains for my state variables. Some are discrete, some are continuous, some are non-scalar. I have to take into account different kind of state variables. Some are always there, some are observable, some are queryable, some you can control, some are exertions, or possibly predictable, some reflect the world, some reflect your reasoning. A hierarchy of action spaces. First, we should leave room for a hybrid representation of actions. I believe that discrete representation of actions or continuous representation of action is not enough. Actions require a hybrid representation. You always have discrete and continuous part in every action or set of actions, even the simplest one, in particular if they are carried in the real world. But even simulation examples illustrate these. So in order to do that, you need the hierarchy of action spaces. And the hierarchy of action spaces is different from the hierarchical organization of your state space. So you may still rely on the same ideas of the hierarchical organization of state space, but be aware that at some point your primitives at the level H can be further refined at a level below until you reach some primitives that are executable commands by your sensor motor systems. That can be possibly continuous, that may have some triggering protocol, some functioning envelope to which you pay attention. So you have to handle this hierarchy of state and action spaces with two classes of models that I call descriptive and operational. So you can have domain-specific and domain-independent models in both. You can have deterministic and non-deterministic models in both. I believe this is not the main distinctions between the acting and planning part. The main distinction is between a class of models that I call descriptive and the class of models that I call operational. The descriptive model is what you are used to. This is your predictive functions, where what is the state that I will end up if I choose A in S. And the operational model tells you that if you are in S and you wish to reach S prime, here is the action that you should do. The problem is that this S and A, this set of states and actions, is different from this set of states and actions. They are at different levels of the hierarchy I just mentioned. So this kind of model describes possibilities, this kind of models describe skills. This is used to predict, this is used to affect your know-what and your know-how. There is an analogy that I find clarifying, which is the analogy between forward and inverse model. I believe that there is some ground in this analogy, descriptive models being forward and operational model being inverse. Let me explain the forward and inverse model for those of you who are not familiar with control and kinematics in particular. So this is the kind of schema that you find in many elaborate robotics control systems, where you have a model that tells you, basically the inverse models tells you if your desired state is some S prime and you are somewhere, here is the command that you should apply. So it is mapping from your effectors to your joints that tells you the command that to apply to each joint. The forward model is the opposite. This is the inverse of that one. It tells you that if you apply these commands to this state, you will be there. And this is used to predict. And you combine the two. This is your command model that tell you how to command your sensors and actuators. And this is the model that you use to predict. In the control techniques that I have in mind, this is mostly used to have a more robust control with respect to prediction. Because you control with respect to you have predicted. You have sent your command both to your predictor and to the actual sensors and actuators that allow you to better focus in case of discrepancy. Why I'm mentioning this schema is that a number of neuroscientists find it plausible model for how the brain works in the motor control. In particular, the work of Daniel Wolpert at Cambridge argued that for its neural implementation in the brain. Wolpert has several papers that explain how this works in the brain. The main point is that the two types of models are used simultaneously. You need prediction and you need the inverse model as well. So let's go back to our business of planning and acting. And my point is that the descriptive models we already know how to handle, the operational model. So descriptive models are at some abstract level. We know how to specify them. We have powerful expressive languages for that. The operational models are more difficult to get. This is also a reason why we have not coupled them enough. So how to get the operational models? The usual way is specification, learning, synthesis, parameter estimation. I believe that we should combine some of these, in particular specification and learning, through mixed approaches. The partial programming approach with the ALISP system developed by Stuart Russell at Berkeley, or the adaptive behavioral language developed by Simpkins at Georgia Tech, offer examples of ways of generating such operational models from partial specification and programs and learning. So what are the planning and acting functions on the basis of these two models? Well, on the basis of the descriptive models, it's very classical, and we all know that. I have a library of descriptive models, a problem. I generate a plane through prediction and search, and my argument was to reinforce prediction, even if it makes search more complex. At the acting level, I have a library of operational models, I have an action to carry on, and I need to maintain my input stream of percepts and actions and output stream of commands through a closed-loop interactions with my environment through sensors and actuators, taking into account this word model of facts that represents what I know or what relevance happened in the past. And the functions here are mostly in terms of refinement of my actions into commands in order to react to new tasks and events, and this requires the choice of refinement and parameters. There may be some reasoning and look ahead to do here. That's why there is deliberation. You have to handle concurrency, you have to synchronize, dispatch, interrupt, choose the right parameters, and so on. But the reasoning part is in most of these steps. So these are the reasoning functions that you do. What are the tools that we can rely on in order to do that? Well, for planning, we have all these representations and the tools that go with them. I'm not going to develop them. I believe that you are all familiar with them. And from the example of PlanX, I believe that I need to illustrate some of those that may be less familiar to some of you. So this is the counterpart of that at the acting level. So RAP is the reactive action package developed by Jim Ferbey in the late 80s. RPL has been developed by Drew McDermott. Again, Drew, this is the reactive plan language by Drew in the early 90s, 91, I believe. PRS that has been developed by Georgiev and Ingrat at the same period. TDL has been developed by Reed Simmons at CMU. TDL is the task description language. Casper is a temporal executive taking into account time and timelines. It is the temporal executive of Aspen. It has been developed by Steve Shen and his colleagues at NASA GPL, and still in use with Aspen in a number of things that Steve showed me yesterday. These systems are more automata-based systems. Procosa is based on PetriNet. It has been developed at Onera by Catherine Texier. Plexil is also automata-based, developed by Vandy Verma at NASA GPL also, and Beeple has been developed by the community of the web services. It is the business process execution languages. In various representations through rules, through functions, through procedures, through scripts, timelines, you end up being able to describe skills, operational models in the way that I define them, that are specified as concurrent task networks with decomposition and synchronization constraints that can be quite elaborate, this decomposition constraint. For example, a lot of synchronization constraints are proposed in TDL. You may have explicit and or implicit word model. You may not have an explicit word model, what I denoted F, in a system like TDL, or in these systems, the automata base, because it's part of the set of the automata. It is explicit in PRS, it is explicit in Casper, and in the RAP as well. You have possibly alternative choices, in particular in some systems like PRS or RPL. These systems can be non-deterministic, and they take plan as input. So they are meant to be executives in an architecture like this one. This is the 3-tiers architecture where you get a planner generate plans, and you have a number of skills that allow you to refine these plans and to react to events. This architecture has been further elaborated into numerous other architectures that are surveyed by David Cottencap and Reed Simmons in 2008. So we already have a rich ground. What we need is to tackle these coupling problems, and a number of systems have been proposed, because I'm certainly not the first one to say that we need to put more reasoning and deliberation at the execution level. I'm mentioning some of them here. So the ACT system has been developed in the mid-90s by Wilkins and Meyers, Karen Meyers and David Wilkins. Propis has been developed by Félix Ingrand and Olivier Despies. RMPL is the work of Brian Williams and his colleagues. T-Rex has been developed by Kanarajan and Frédéric Pi. This is something more recent. CRAMPL has been developed by Beats, Michael Beats, and TST by Patrick Doherty. These systems are of the last couple of years. T-Rex is maybe a little bit older, 2009 or 2010. ACT goes back to the mid-90s. So all of these systems try to put some of this and some of that together. For example, ACT relies on PRS plus HTN. But however, it is just a wrap-up language where your procedures are clearly decomposed into a partition, where some of the procedures are seen at that level and some are seen at this level. The marriage is not, or the coupling is not really addressed. Propis is also based on planning on top of PRS with look-ahead mechanism with a state space planner. T-Rex extend the architecture that I just saw you, we just seen in the previous slide with an executives toward several such executives or reactor. So you have a distributed set of reactors. Some of them do rely on planning. RMPL and T-Rex use temporal reasoning. CRAM is the cognitive robot abstract machine by Michael Bees, plan language, cognitive robots abstract machine plan language. It is something that follow up on RPL with some plan editing mechanism. To my understanding, I haven't seen look ahead and reasoning in CRAMPL. TST is something recent that has been developed by Patrick Doherty. It is mostly at the base, at the level of planning, not much, in my view, at the level of acting, and it extends, this is the task structure trees, it extends the task trees that are present in TDL. So number of numbers, a few interesting representation, maybe RMPL is one of the richest in my view, where Brian and his group have developed number of constructs with conditional temporal plans, reasoning of these conditions in the temporal plans, with probabilistic temporal plans, and risk assessment on the basis of this probability, on the basis of these probabilistic plans, as we saw in a paper yesterday in this conference by Santana and Brian. So we already have a rich ground of things in between. I forgot to put the references. Yes, here they are, of the contributors of these various systems and the dates. So we already have a rich set of representations and tools that goes with representation. I believe we need to have a better grasp about what they do and better integration with the other reasoning and planning developments that are in the field. And maybe this can be developed with something that I call refinement method, quite simple and amenable to teaching and further elaboration on the basis of what I mentioned. A refinement method, we know what they are in planning. It's just a triple of task preconditions and partial order of subtask. At the acting level, it's something similar, but you have a triple where you may react to some event or a task, a precondition and the body. The body is richer. You may have control steps, assignment, subtasks, and commands. To make this a little bit concrete, in pseudocode for a language that does not exist, it's just to give you an intuition. The open door example that I mentioned earlier refer to a task that is refined into two subtasks depending on the nature of the door and some preconditions, which is to unlatch, then to throw wide the door, with a number of commands that are to move close if the door handle is not reachable, to do some monitoring. And the unlatch can be addressed by diverse methods depending on whether the door opened left or right, away or toward from the opener, and other conditions, whether it slide and so on. And again, it refines the task into commands and other subtasks, and the same for throw wide, depending on the nature of the door that can be described in this simple language. This is just to show you that this language relies on state variable, can rely on something very familiar to all of us, and can be plugged in one of our planner, and it can live with other methods that deal with events such as an emergency here, and take a number of steps, refinement steps with regards to these events. So, planning refinement methods at the acting level, you can handle them with some non-deterministic interpreter that can be quite simple, plus all the synchronization and time handling constraints if you have explicit time, and I believe most of you may need that in many situations. So you have concurrent threads of refinements that are going on in parallel. So you have an acting system, library of methods, your world set of facts, and your stream of input of tasks and events, and output stream of commands that interact with the environments. And in order to do that, on the basis of your refinement methods, you maintain concurrent threads of several refinements that handle the new tasks and events that arrive. And you have to choose, so there can be reasoning and search at this level methods for addressing your concurrent tasks, subtasks, and events. And you progress in parallel on the topmost method in each of these threads, taking into account assignment, control steps, command, and further refinement. And if needed, you retry other methods. So the schema can be developed in a simple way and made progressively more rich and elaborate. At the planning level, you have to enrich what we call commands here with a predictive model, with a description of what this command may give you. And you can do that with precondition effect operators or with simulation models, which is even better because it may address more elaborate commands with the usual search and look ahead. So the global picture is the following. You have axing, your input stream of tasks and events, commands, library of operational models, and your world set of facts. And you may have to face a mission that requires further planning, and you trigger further planning with respect to this mission or goal that refines it into tasks. At some point, you have to choose between methods, and you trigger the appropriate planner that takes into account where you are with some look-ahead mechanism and give you the appropriate methods. And this can be deterministic or non-deterministic, the same for that one. And you can have also domain-specific or domain-independent one. So the picture puts planning in the middle of the scene, axing, sorry, in the middle of the scene, with a number of planning techniques and systems to allow further deliberation on the actual task and actions. So this is the global picture that you can reach with sample representations like the refinement method that I mentioned. And with that, I believe I can move to my conclusion and the challenges. So the take-home message that I would like to underline here in this slide is that axing is different from execution and planning, that you need knowledge representation and reasoning on actions and events that are situated in context with prediction capabilities. And for that, you have to couple planning and axing. You can do that through a hierarchy of state spaces and action spaces, and with a consistent coupling of descriptive and operational model. I believe this is probably the most important part of the take-home message. You need to couple descriptive and operational model, what allow you to act and what allow you to predict. And I illustrate this with refinement method that can be organized into something like that. So this is the take-home message. So there are a wealth of approaches and techniques available around, in particular at the planning level, some at the acting level. I mentioned a few. There are also numerous open problems and in the issues that I address that can give ground to many of you for to express your talents and the long careers of good science, and several open problems in issues that I have not addressed. Let me start with the challenges and open problems in the addressed issues, just a few examples. I mentioned several times the need for domain-dependent and domain-independent coupling, in particular for task and motion planning that has been illustrated in this conference and becoming a very better understood problem. But we have several other domain-specific plannings that have been mentioned in this conference coupled to task planning, for which we need to further progress. We have to integrate our planner in our planner hierarchy of state and action spaces. And this involves a lot of challenges, in particular at the search approach, where the angelic hierarchical planning techniques can be can offer good perspectives if we can understand how to upper bound and lower bound the set of reachable states that are needed in these kind of techniques. We have to integrate goal and task reasoning in refinement methods. The refinement methods are triggered by task, but you may express what you want in terms of conditions with respect to your states. Some directions of work in the Gödel planner by Dena and his students have been proposed in the last ICAPS. Dena and his students at the last ICAPS, and work is going on. You have to come up with way of gating your refinement methods, both from the viewpoint of descriptive models and operational models. And I mentioned the coupling between synthesis and learning and possibly partial programming. And you may have also to express meta-knowledge for your refinement methods in order to check the consistency between the two levels, descriptive and operational. I mentioned situated automata as a possible avenue of work. There are several unaddressed issues in this area of coupling, planning, and acting. In the survey paper that I referred to in the introduction that we wrote with Félix Ingrat, the global picture of what's going on in robotics involved to distinguish not only the interaction between acting and planning, but also observing, monitoring, goal reasoning, and learning. Observing, there are numerous challenges, not only at the planning to observe the anchoring problems and so on, monitoring the synthesis of what you monitor and how you monitor that. Goal reasoning has been illustrated by several papers recently, and including in this reference, there is a paper by Mark Roberts on that, and learning, I mentioned that. I'm not going to get into the challenges that arise in having this global picture from the actor's point of view. I would like to finish by going back to the discussion, the community meeting discussion of yesterday about how to organize our work for addressing these wide challenges. And I was very pleased to hear a number of proposals in that directions, in particular with respect to a repository of challenging problems. Probably these problems have a wider granularity if we want really relevant problems, that the kind of problems that we are used to. Hence, we have to organize contributions around low granularity, so problems on which one can work reasonably for 1 year and get some results. And the solutions and contributions to each one of us have to get assembled into consistent pictures, has more tool sharing, and the discussion that went yesterday at the community meeting was very interesting from that point of view. With that, I would like to thank you for your attention. Jane.
Well, so first of all, thank you for a very, very insightful and very interesting talk. I have a lot of things to say, which I'll say a little bit later, but one thing that I wanted to say was that with respect to your initial take on planning and the notion that planning can somehow be sort of separated from a lot of these other considerations in some contexts, I actually find that sort of unfortunate for the following reasons. Even if I don't have to build an explicit actor or command system for, say, design. And even if I have a very, very complex problem with one action, like Michael Korkendorfer's ACAS, these are problems where I think we have overly trivialized the planning problem. And so my suggestion is that we can take everything that you've said about cases where you really do need to design low-level commanding, what you're calling acting, and what you're calling planning, and integrate them. And this is a valuable thing that even people who do planning, which looks like it's divorced from all of those lower-level issues, not only can benefit from, but really needs to benefit from. So I'd like to hear your thoughts on that.
I fully agree, Jeremy. Really, it was for the sake of argument, but you're right. We share the same viewpoint on that. My argument of enriching the prediction functions and taking more of a richer semantics of action goes exactly toward what you are asking for. We fully agree.
So actually, very quick follow-up on that.
Yeah.
In these, in many of these sort of operational contexts, this notion of prediction that you're talking about, or simulation, is really, really important. I won't put words into Mark Giuliano's mouth, but the two of us had a discussion about that very thing. Yeah. And that's a place where you really do have this execution and acting context that sort of looks like it's separate from your planning, but PDDL, even the richest forms of PDDL, cannot express the kinds of complex constraints that need to be simulated once your plan is done. So I think I'm totally in agreement with you there.
It's not a matter of complexity of the language or richness. It's a matter of the type of what the representation is meant for. It's not meant for predicting. This is the operational type of models that I am referring to.
Thanks, Malik, for a very interesting talk. It reminded me a little bit of, I guess, very prehistoric work by Phil Agri on the separation, the distinction between the view of plans as programs and plans as advice for an execution architecture. Yeah. That it's very easy for us. It's a little bit connected to the comment that Jeremy made. It's very easy to evaluate programs. They can be correct or incorrect. They can be optimal and so on. But what is good advice is a lot harder to evaluate. And just to disagree with Jeremy, it's sometimes possible to show that the best advice to an execution architecture is the cost optimal plan. And then you would want to go ahead and compute that. But I agree that in the more general case, the advice needs to have other characteristics. So how do we start to evaluate plans, viewing them in this more general context?
It's a good question. I haven't thought about, but it's very relevant, the work that you are referring to, very relevant to the view that I presented here. You're right. You have to consider a loop where your advice-taking system is integrated with your acting system. And if your advice-taking system in particular is being used in some way or another to help you learn better your operational models, then it goes with this kind of partial programming techniques to which I refer that can be coupled with learning. So there is a lot of good questions and directions of research there. But the advice-taking techniques, planning from the advice-taking techniques is certainly very relevant. In the global picture that puts acting there may certainly benefit from an advice-making planner. Yeah.
Okay. Thanks for the very interesting talk. I have one comment and one question. The comment is that I'm happy that as one of the PlanRob workshop organizers that a lot of open issues and unaddressed, let's say, topic are actually covered well by the papers presented in the workshop, and this is more a comment on this. And the question actually is if you can comment about your, let's say, approach or idea with respect to the approach that was first in IDEA architecture and then in T-Rex architecture about the multiple reactors. So of having different, from a more deliberative to a more reactive multiple sense plan act cycle running concurrently. So
Yeah.
how would you relate your concept here in this regard? Thanks.
First, congratulations for your work, Andrea, on the Plan Rob workshop. It went on very well, 2 years in a row, and I wish you a lot of success in the following up of Plan Rob. Now, the distribution issue, I haven't addressed that at all. It adds another dimension. Indeed, T-Rex is a number of reactors. Some of them do have access to planning facilities on the basis of these 3-tiers architectures distributed over several reactors with coordination, synchronization, sharing of variables between them. It adds an interesting dimension. Can be quite tough to model a system in that. I believe you have an experience, and it's really an open problem. I'm not sure that every actor has to be thought of in the centralized way that I have presented, mostly for the purpose of arguing, and the distribution aspect is another dimension that one has to take into account. Again, it is a very interesting approach that has been developed in T-Rex, and today the limiting factors is how to model and how to debug your models and so on. It's quite difficult. I had the visit of Frederick P. recently, and they are finding it more and more difficult. So it's not obvious that that's the best way of addressing the design of a complex system such as the rover for the moment. An open question. Please.
That was a fascinating talk that brings up issues that go back 30 years, I think. One of the things in terms of the way you're organizing this, so yeah, you can go back to IDEA or T-Rex or the 3-level architecture or Forbin. I mean, there's a huge number of these. But one of the claims that some people have been making as a way of resolving some of these is that what you need to do is to incorporate an execution semantics all the way up into the top level of planning. Okay, so for example, Dave Musliner's Circa architecture, or the work a bit further back that Chris Elsesser did on the adversarial planner. Okay, so that you need a representation for planning, no matter how abstract, which actually allows you to reason about things like the fact that the action might not work, or how you tell that the action worked. And what I'm curious about is when you're talking about these coupling problems between planning and acting, is that an implication of this? That if you don't have a way to represent the actual execution of the plan that you've synthesized, then you don't really know what you've got. I mean, do you need that execution semantics in this top level?
It's a good question. The answer that comes to my mind is that if we need to prove something about the execution of systems, and we certainly need that in critical applications and so on, the perspectives that has been developed that are referred to by Stanley Rosenshine of the theory of situated automata, where you express, I believe you are referring also to the same kind of line of work, is really needed. And this is one way of allowing you to reason off what you have implemented to your operational models. Because in a way, your operational models are not explicit in their behaviors. So we know more now in formal automata theory than at the time of no more, and have more powerful tools to allow us to advance in that directions. And we need that. I believe if we can translate our operational models in terms of these refinement methods or some other means formally in terms of specification, we need that in order to be able to analyze what we have designed. And I agree with you, it's a very important point.
But that sounds like what you're saying is there's actually you were arguing for different representations or different ways of reasoning for planning and acting. It sounds like what you just said is there's a single most abstract formal model underlying all of this, because if you're not doing all of it in something like the context of situated automata, then you're getting it wrong?
I'm not sure that this is this is easily feasible and the appropriate way in general. Yeah. What I'm considering as an avenue of work is this coupling of operational and descriptive models, plus some mean of describing what you have put in your operational models, because the descriptive are already contain the kind of information that you are mentioning.
That would be nice.
That
would be nice.
That would be nice. So we can talk further about what we have done in expressing in a formal language like BIP, on which you have a lot of proof mechanisms. That's the work of Félix and Grand, ways of proving the executive mechanism. So this is the kind of perspective that I see.
Okay.
Translating and using formal tools such as, in this case, it's not a model checker, but something similar to the BIP system, to allow you to prove your executive or your models at the operational level.
Okay. Thank you.
Thank you.
Malik, thank you very, very much.